Okay, so we're in the final section of our course. This will be another look at trace analysis and collection tools from the US Supercomputing Center, which is a complement to the tracing and trace analysis tools that we just saw from Barcelona. As I said, my colleague Mark Schluter will be presenting, and so I'll turn it over to him.
Thank you, and good morning to this last session for the day. And as mentioned, we were looking at Scalasca trace tools and how they interconnect with what I showed you yesterday about the profiling side and how we can extend this to the tracing. And at the end of it, we will also see a short overview of the Vampire analysis tool, which is a timeline viewer with similarities with in features what Paraver offers. But just as an outlook, which we see at the end, the main topic will be Scalasca and its tracing capabilities for now. And basically, it's a performance toolset for the most popular parallel programming paradigms. Our current focus is MPI OpenMP. We have support for POSIX threads to a certain degree, but the GPU side of things is currently limited to the host side events. And there's some care to be taken if you want to do measurements on that side. It's a work in progress, and at some point we hope to have full support for GPUs also in there. The specific target of Scalasca is running large-scale applications. It has demonstrated scalability up to 1.8 million parallel threads. So it's looking at the big picture of communication and synchronizations on a large scale. But of course, it also works at small, medium scale, which is something we will be looking at for demonstration purposes. The latest release is 2.6.2, is from April last year. So what is the idea behind the automatic trace analysis? So the idea is to let the application look for patterns of inefficient behavior automatically. So, and classify behavior in certain elements in terms of significance. And additionally, show the actual root causes of the certain delays you can find in your trace measurement. So conceptually, it's the idea to take the huge traces we can get out of measurements, in particular if you're going to large scale, and condense it down into a high-level result with the properties you're looking for. And the result will be in the cube format, demonstrated at the same level of metrics we have seen with the summary reports. You have your property, your call path, and your locations, and the data is presented in these kind of terms. And we will see later in the demonstration what kind of elements are added to a cube file that are contributed by the trace analysis. It has the advantage to cover the entire trace always, and it's running through on the same scale as your application program. So it has the benefit of using the parallel resources you're running your application with. And can, on large scale, be quicker than manual than visual trace analysis. Also, the visual trace analysis, as shown before with the BSC tools, or what also Vampire makes use of, has the advantage of being visually significant and what you can recognize with your own eyes and the patterns you can see there. But if you're going large scale, it's good to have a numerical result and something that covers the total traces. So in general terms, it's open source, it's a 3-class BSD license and supports all major HPC platforms. It relies on the Scorpio instrumenter as a measurement library and provides additional convenience commands that control the measurement as well as the analysis. It supports the data formats I also mentioned for Scorpio, OTF2 and Cube4, while the OTF2 event traces are the input for Scalasca, and the Cube4 format is which is the output format which we are presenting our results in. The current limitations are that we can only deal with MPI traces below thread funnels because we need to match basically the communication patterns, and if you are communicating too freely on your threads, we cannot assign and really match communications to each other, or at least potentially, and this can lead to problems. And currently, as mentioned before, there are limits to the GPU support, and in particular events that contain executions on non-CPU locations. PAPI metrics, like we saw for the summary, are currently ignored since they are not actually used. They are not integrated into the results. So after basically some basic meta information, how does Scalasca fit into the overall workflow? And we are basically starting out with the score P measurements. Like we saw yesterday, you have your instrumented executables and build your application. And the first step that we always recommend doing, because you have to be specific when you're doing tracing, is doing a summary report. So get the big picture, look at it in your cube file, what the profiling does provide, and then basically refine your measurement configuration based on the information you got in your first measurements, and then do the tracing run with a parallel trace analysis, and then the report which is written out by Scalasca as a trace analysis report, which then again you can look at in the Cube GUI and explore the additional information that you are provided with. So when we are talking about the Scalasca trace tools, it's technically the step of local event traces, gathering local event traces, the parallel trace analysis, which is appended to the actual execution run, and then the analysis and the writing of the trace analysis report. So the question, we're doing automatic measurement and problem detection. What do we actually want to measure? And the first cornerstone of our automatic analysis is wait states. And wait states are times that we can measure and calculate where we know that this time is wasted because of the order of events that happen. We have here an example of the wait state late sender in the relation from an MPI send and a receive communication on two processes. If we see that the MPI receive is started before the MPI send even is started, then we know that the difference between these timestamps is a wait state definitely. We cannot promise or know specifically if the time beyond that is productive or how much time is overhead in the construct, but we can definitely determine that this is a lower bound of time that we are wasted in this communication. And this can happen for various reasons. In the time balancing before, why the MPI receive was earlier reached than the MPI send. For anyone who knows MPI, we know that there are various variations of MPI calls, non-blocking and blocking communications, and these wait states can be calculated for both blocking communication as well as non-blocking communication. You just have to measure certain different cases. If you have a non-blocking receive, you're basically checking the wait time when for the early arrival of the MPI wait and the communication pairing with the MPI send, and then you see, okay, this is a time we could have spent more useful in computation, for example. And basically these wait states in their form show you hints of time where you have a certain wasted time on something that could be used better. And through optimization, rearranging of computation, other elements of your algorithm, you can basically shift your communication pattern in these cases. And this also highlights the topic of the performance cycle I mentioned before, that once you fix one wait state, which if it is large enough, you might have to recheck your measurement because sometimes the wait states then travel to a different portion of the program. And so rerunning your measurements often enough to check that your current measurements are actually current is quite useful in these cases. Another concept, which is basically an extension of the wait state concept, is the critical path, which is basically the path through your program which is responsible for the program's wall clock runtime. So it has the longest execution times, and the other processes, like we see here, the orange wait states, are basically waiting on these elements of your execution to finish. So this is part of the effort to give you hints where to optimize first, because these are candidates that have the chance to bring down your overall wall clock time directly, while optimizing other elements where the processes are currently waiting anyway might not have as much of an impact on your execution in these cases. So it's trying to hint you which elements of your program are actually effective to optimize. Then another extension is the question, what is the root cause of your delays? So if you're having just one simple example of a late sender where you have two communication partners, it's easy. You have a direct relation, which one is waiting on which. But if you have multiple communications that are chained together, like with these three cases, three processes, and then you have wait states that accumulate based on direct and indirect waiting time, because the direct time is always concerned with the direct partner of your communication, in this case these two, and this is the direct communication, the direct wait state, or in this communication the actual portion which is direct waiting time is just this bit, while the remaining waiting time is indirect waiting time inherited from the previous communication partners. And so you can calculate the delays that are basically the root cause for your actual communication problem, so that you don't need to, even the first, when talking about what to optimize first, people are encouraged to pick the biggest contributor in total, so the biggest wait state. But since it's a wait state that is constructed out of a sequence of events, actually finding the root cause for this delays is more important and more effective in optimizing your code. So if you're fixing the root cause delay, which takes the causes all the other further delays, you are better off in your overall optimization process. These are the major, topics we have, the analysis targets of our analysis. So we have the wait states. We have I showed only the late sender, but for all the communication patterns, we have various different patterns that we analyze, and I can show you in the results a few more when we are doing the demo. And the critical paths and the delays are based on the additional information that we are getting from the wait states, and then looking forward for the reasons and the better optimization targets. And now we want to look at it, how do we get there from a practical standpoint, and we are switching to the demo part of the session, and we are looking, sorry. So since I mentioned I showed the workflow, we are basically starting from the profiling run first, which we done before yesterday. But just to introduce you to some of the um, tools that Scalasca provides. One is the scan, or the prefix Scalasca Analyze, which offers the option to run your measurement with the Scalasca Analyzer. But it also allows you to run the measurement of a summary profiling measurement as much as a tracing measurement. And since it's a first step, we can just see how to rerun it with Scalasca. And in the same fashion as we are using SCORP to prefix instrumentation, we are using scan to prefix the srun command, so the scheduler command right now, to run the MPI command to run the measurement. By default, it's a profiling measurement. And just to get started today, we will repeat that. And while that is running, I can tell you Scan uses SCORP underneath to run the measurement. So you can change options based on the SCORP environment variables, as we seen yesterday. And for some elements, these are only options available. But for some specific cases like profiling, tracing, etc., you can also use parameters from the scan itself. If you're looking at shortly at scan, you have the options to run the tracing, you have run the profiling, you can run quietly without it, and you have also the option to skip the measurement part and just reanalyze your measurement that you already gained from a previous run. So we have here our run that we basically did with the similar settings as before. And the only difference when running the scan is by default it adds some output from the scan side with the configuration it ran and how long it did run. As is still 14 seconds and is the same basic overhead as we did before. And the next step, since we already refined it and we also learned yesterday that we did something like 200 megabytes for tracing. The variables to set is basically the SCORP total memory, which is, I just set it to 250, and scan itself has also own options like analyze options. And this time we are using time correct, but I won't go in more detail, but it has the option to fix certain issues with timestamp collection and correct it in a semantic manner. But I don't think that becomes relevant in this case. Otherwise, we are also using the filtering file because only within the filtered fashion we are actually getting useful results for tracing. And now we can, in a simpler term, use -t, -t here. -t to start the tracing. I haven't set an experiment directory because Scalasca itself uses the processes and threads to create a name for the experiment director itself. Like we see here for the profiling run, it did the naming based on the executable, then the 8x6 of process times threads. And since this was a profiling only one, it's called a summary. In terms of additional files, we are only seeing the same files, the manifest, the profile, the config file, and the filter. Scalasca does add the job output to the measurement directory for reference, but otherwise it's the same measurement as we did with the profiling. And now we can start the tracing run, and we can see how that behaves. For tracing itself, the primary consideration is how much memory you have, since you ideally want to store every event you are measuring and recording into memory and only write it once at the end of the run. Technically, there is the option to buffer flush if you have too many events, but as these are process local, they have the disadvantage that they can be disruptive to your execution and will distort the measurement you are getting out of it. So in general terms, once you see warnings of buffer flushes in your measurement, you should generally rerun your measurement with a higher set of total memory if possible, or stronger filtering to reduce the memory requirements. So now we have a new measurement. It's called trace, and it contains the elements from the profiling run. Since we didn't disable profiling, it still runs with profiling as an addition. If you want to reduce a bit of overhead and distortion, you can run with tracing only. Then the Scout Cubex is added as the result from the trace analyzer and has its own assigned log files. And then you have the raw trace data, which is the traces OTF2 and the traces folder. The traces folder is just for reference, contains traces, local traces for every process, which contain a definition file and an event file. So you have double the number of files as your scale is, basically. It's something to consider if file system issues are a problem. Since we are now in the stage we have a measurement, as you might remember from yesterday, we want to remap our measurement to get a fully set of metrics and refined measurement. For this situation, Scalasca offers an additional helper tool, which is Square, which will take the folder as the input and remap anything which is in any cube file which is in there, and then try to start cube GUI on the remote X if it is available. In this case, it's not available. I'm using the option -S to avoid the starting of the attempt to start the cube file, and it will just generate an additional copy score file. And you see basically the output of the remapping is hidden, but you see that it's post-processed the summarization report of the profile and the trace analysis scout, and we see now inside the trace folder additional files. That is the trace cubex, which is the remapped report of the trace measurement. So now we can have a look at this. Let's see. Yeah, I'm switching to the GUI. We are on our Jupyter lab here. Let's see. We're now in the folder, and we now have the trace folder, and I can open this one with my mouse does strange things. At first glance, this will look very similar to the summary measurements we saw yesterday. We still have our 3 panes, we have metrics and our locations here, which is the same as before. The main additions of our trace analyzer happening on the metric side of things. First, we see on a few new metrics, as just going to the ones we mentioned in the slide sets, we have our delay costs, which are basically showing the delay costs for MPI, OpenMP, and you can see how they are attributed in the call tree to different regions, how much they are concerned with these delay costs. The same holds for the critical path as additional information, which is providing information how much certain calls and call paths in your application run are on the critical path and so far are interesting to reduce in your execution. But the main element or the root element of our general analysis are the wait states, and they are added to our time tree, which is subdivided as before into the different paradigms. In this case, something like the MPI and OpenMP. And we have now new wait states that are children of the different paradigms and their subdivisions like collective communication, point-to-point communication, or synchronization. And you also see this for MPI and OpenMP in this case. Let's see, we have here barrier synchronization, for example, which is a wait at barrier. And let's see, we can see, for example, our main solvers in this BTMZ is basically MPI open parallel, and the wait at barrier happens inside these parallel regions. And since we saw this behavior before in the last in the presentation for the summary measurements, that when we are looking at pure percent, we saw that the behavior of these threads is that the first 2 threads have enough work to do, and the last 4 threads don't really have that much to do in these OpenMP regions. And the wait at barrier is basically the more or less the inverse, since they have not that much to do. The last 4 threads are highly busy with waiting in barriers. So we see this behavior in the barrier behavior for the wait at barrier. And if we are looking at something else like the late sender I mentioned, you have to pick basically the function calls that are happening for the point-to-point point-to-point communication, and in this case, it's the happening in the wait all of the MPI communication. And since it's only happening on the master thread, you're happening on only on the first thread of each of the processes. These are, I only presented the late sender in the slide set, but as you can see, there are quite a few other patterns, and we provide additional information that should be here. But something with the online. Technically, in this category, the metric documentation is online documentation of our metrics, which basically explains each of the for some reason the could not be loaded issue you have to ignore for now. But in principle, you have additional documentation about each of the patterns, and there should be available for each cube installation and reachable technically. It's mission option for local as well as online access to documentation. When we are looking at the metrics, we also talked yesterday about POP metrics, and one of the things I mentioned was that some elements of the POP metrics weren't calculated for profile measurements alone, the serialization and the transfer metrics. And this is basically now available in the POP Advisor plugin, which is providing the information. And we now see that we have serialization efficiency and transfer efficiency getting these from the trace measurement itself, because we needed the time information that was stripped out of the profile measurement to get this information. Since this measurement and Scalasca itself ignores the PAPI counters, we don't get any information about IPC. And that is the reason why we offer an additional tool for getting PAPI metrics, or in general for getting POP metrics, or in general more complex use cases. And this is a multi-run option for Scalasca. Let's switch to the demo site shortly. We offer a lightweight multi-run feature which allows you to run multiple measurements at the same time and then combine them together into one measurement that holds all the information. For example, in this case, we had the issue that we didn't see the PAPI counter, but the PAPI counter are provided for the summary measurement. And so mixing them together is the basic concept behind the multi-run. The second element of multi-run is that in many cases you want to run multiple measurements and take the average to have a more statistically sound measurement to avoid system noise, for example, and get more firmer number on certain elements. So this is also an option that you can choose when doing multi-runs. So you have basically the option to set a set of Scopy variables to get a certain configuration for each of your runs, and then decide to run multiple times. In the specific case of POP and the POP metrics, we have decided to offer a preset basically for that, and it's the first use cases of presets where we say, okay, this is a combination of variables and settings that we want to offer, and we want to make it as easy as possible for people to get these metrics in its entirety and the collection for that. And so we offered additional setting to the scan that where you can choose -P in the preset, and in this case of POP, it will run a certain configuration that produces an example with multiple measurements that contain all the metrics. And I can show you how this would look like in practicality. We have the Scalasca job, and instead of the simple -T, we are choosing now the scan -POP -P POP, and then the srun as before. And what this will do is that it will run now multiple measurements, in this case just two, a profile and a trace measurement. And then our square tool also allows the option to merge these then together, so that's the principle the same steps you have as before. You have run a scan and then a square, and you have your complete set of measurements. This should run not much longer, technically double the time because you're running two jobs, but it will, since the overall runtime was just 15 seconds, it should be rather fast to finish. And if you're looking at what you are getting out of it, we have a new naming scheme where the preset name is added to the directory and then the number of configurations that we are running. And we are getting inside this two measurements with the two configurations. And we are also getting output of what the configuration is used, what it looked like. And this is basically the interpreted settings that we got from the preset. It sets some default values that hold for everyone. And then we have two run configs that have specific settings. One, we have a tracing run without profiling, and then one profiling run without tracing. And the profiling run actually contains the PAPI counters we shown before. In principle, you can now take this config file, useSmith with -m, and run it yourself without using the preset, and you can change variables in it if you want to change for specific outcomes. So since the job is through, we now can use Square to again remap our output. And in this case, it will be outputting and will remap and combine the trace and profile measurement. Let's see what we now get here. We now have an combined Scout plus profile QBEX, which is the unremapped form, and then remapped into trace plus summary QBEX. And if we are looking at this in let's use the same one, open new file, we navigate to the POP preset output and see trace plus summary. So now we are getting the information that contains the collected information. We have the counter from the summary measurement, and we have the something like the critical path and the delay analysis from the trace analysis. And if you are now looking at the POP metrics, you're getting your serialization and transfer efficiency, as well as your IPC, instruction, etc., and counters. So this is a way to combine multiple measurements into one and then have a combined view of all of the metrics you want to look at. Sure, there are some limitations. We are currently working on extending this to GPUs so that you have full GPU measurement on the one hand and mix this together with the trace analysis. The other limitations, you have to have relatively deterministic runs between two instances of the same application. If your application runs very widely in terms of what your call tree looks like, then you're running into issues of merging them cleanly together and having useful information out of it. So it's always something you have to take care of, but similar issues you have if you're simply looking at multiple executions and they behave very widely different, you have issues anyway. So let's see if we are looking at the in the slides you can see then this is a bit of information about the format for the config files. We have a global section, we have then run sections per run, and we have then a few more informations how they are defined. If you have an interest, you can look at this offline when you're getting the slide set, access to the slide set. And as with the case yesterday, we have a T-Leaf API plus OpenMP study that shows similar features of this Scalasca analysis in following parts. But with this, I want to close out the part for Scalasca and switch to giving a short presentation of Vampire to close out this session. Let me see. Um, Uh, this is just a short introduction to Vampire, and with the caveat, this is a commercial tool, so the availability is always depending whether the sites already have a license, and there are technically, I think, some demo versions that you can get, but I'm not sure. It's developed by our colleagues at the Technical University in Dresden, and the offshoot, the Gesellschaft für Wissenschaft und Technologietransfer. So it's just a high-level overview to basically cut back to the comparison with PowerWare, where we have a timeline view, and will see some similarities in the general functionality. And it helps as a complement to the Scalasca analysis to have the timeline view as a visual aid in terms of analyzing your codes. So we basically, that's the approach. We will use them in complement and to supplement automatic analysis. And you can basically go from one to the other by saying, okay, this is an interesting pattern we saw here, and might see the numerical analysis on the other side, or you found something in the numerical analysis of the trace tools and say, okay, let's look at this instance in Vampire. It starts out with a classic timeline views, but also has summary charts and that provide quantitative results for the current selection of the interval. And on the technical side, you can run a Vampire as a local installation on a local measurement, which is then limited for practical reason more or less to small, medium-sized traces. But if you have very large traces, you're looking more at a constellation where you want to run a Vampire server, which itself is a multi-process program, which then reads in the very large trace file and supplies you with a connection to the Vampire client. So you have a similar concept as we are using with Cube. If you're connecting to very large files on a system via a local client to a larger server. It has its own challenges always connecting to a system, but once you're doing that, you're basically just looking at the aspects you are currently focused on, and the experience is more smooth than trying to open a very large trace file completely locally. So the main elements of Vampire is the master timeline chart and the process timeline. It is enhanced by counter timelines. This is where the counters have the advantage that you see the distribution over time, which is lost in the summary information on the profiling side. And you get additional information where you summary chart about the functions, the messages, processes, and the communication metrics. If you're opening Vampire, this is basically what you see from the first time, and you will stay in this singular window, but subdivide it and add additional information. At the top, you have the navigation toolbar, which always shows a very high-level view of the total application, and is basically just to navigate you where your main timeline is selected. So you are selecting one area and then focus in on the information. In the master timeline, you have basically the list of processes and can scale and zoom in the X direction for the time and on the Y direction for the processes and threads. And on the right side, you have additional information. So the color coding is based on function groups that have a default color grouping, but you can assign and subdivide further if you are looking at specific elements. And you have basically a high-level function summary, which are the highest contributing factors in this case, which is also a BTMZ. The OpenMP loops are the main elements of the execution time. And if you're looking at the black markers, this is basically the communication and synchronization points. We will see more about the show of communications later. Sorry. You have then additional information like the function stack, the call stack that you are currently in on your current cutout of your execution. In this case, it's the whole execution. But you have basically where you are, which functions are executed, and how they're stacked in your call tree in this execution. And basically can then, that is one of the advantages of timeline views. You can see where your initialization phases are, your computation phases, and select the parts that are of interest for your analysis, specifically on start and begin timestamps. And you can then match together additional information like counter timelines. In this case, there's perf counters from page faults, which can be recorded on the SCOP side and can now be displayed alongside the master timeline. And they are all basically vertically aligned, so you can see which elements are how the values are distributed at cross sections of your execution. And you can have absolute values or color-coded over time measurements and see where each of the process behave over time. And you also see here some of the elements. Once you have more processes, then you have space to show every line. You get the information slightly compressed and selected by similar elements. You can select elements like this function initialize and get additional information about this specific instance of a function call and how long execution, bytes transfers or something if it's a communication call, and the additional information. You also can basically, if you're looking for specific functions and calls, you can highlight them by a search function and fix on certain information that you are getting specific information about. And if you're looking at something like floating point operations, you can see you can have derived metrics based on the input values that you have in your information. So if you have something like cycles and instructions, and you can then combine them and calculate new metrics out of it. And you can see that the computation phase here that we identified before has higher floating point operations than the initialization phase. And similar behavior you see. MPI communication itself is lower in floating point operations, in particular if you have waiting times. These are generally low operation counts, and you can identify useful times based basically on how much the counters show you how much execution happening in actual phases of your execution. And this is an example of basically one early reduced bottlenecks that we would show in Scalasca, but as pattern it shows in Vampire. You see the communication lines and which elements of a call belong together, and then you see which parts waiting on the execution, and you see that it's reflected in how much actual computation is happening in these phases of the processes and different threaded elements, and waiting for actual work to be done. Yes, you can do a process summary and first get a summary of which of the functions are actually contributing the most, but also can gather together the process summary where you have the accumulated view information about functions across processes, and you can group essentially processes by similar behavior and see if they are doing something different over time and how each calls are distributed. And this is an example where you basically can find groups and group them similarly. You see basically a short, very high level icon for how the sets of process which are grouped together, and then you can see that you have groups of processes that behave similarly to each other. That was a very high-level overview just to get an impression. It's basically scalable visualization of event traces, and this similar approach as Powerware, where we're going with color coding activities, and you can easily identify the program structure in itself and pick out elements that are interesting and have a behavior that stands out from an equal execution. And it is a client-server approach to make sure that you can use the HPC resources to actually view also the results. And in principle, it supports also multiple trace formats produced by different measurement tools. We are basically mostly using it for the OTF traces produced by SCORP, but OTF is a wider used trace format, and it can be used also by different information. This is basically what I wanted to tell you about Vampire. And if you want to know more about Vampire, there's the webpage vampire.eu and the email address for any service contact. If you have questions or if you are interested in using Vampire, that's probably the best address for that. So this is basically all I wanted to show you for today. If you have any questions, I'm happy to try to answer them, and whether it's the Scalasca or the general process of our workflow, feel free.